Welcome. Now we are going to discuss about exponential distribution. In one of the previous videos, we have discussed gamma distribution. That is, the density of gamma is either given in this form or the one that I have written here. Okay. So in either of this form, we discussed the gamma distribution, and if we let alpha to be equal to 1 in it, then we have the exponential distribution. And here, as usual, we are going to derive the mgf, mean and variance. So mgf, that is m of t, is what? Exponential of e to the power tx. So it is a continuous random variable. So from 0 to infinity, 1 upon beta, sorry, first of all we'll have e to the power tx, 1 upon beta, e to the power minus x upon beta dx. Okay, this 1 upon beta is a constant, so we take it outside. So interval 0 to infinity, e to the power, we have this x as common, so t minus 1 upon beta dx, isn't it? So when we integrate it, what would we get? 1 upon beta e to the power x times of t minus 1 upon beta divided by t minus 1 upon beta over the limit 0 to infinity. Okay, and here when we substitute x equals infinity, there is a chance that it go to infinity. So what we do is that we rewrite this as 1 upon beta minus t. So it is simply minus x times of. Okay, now that it is 0, so minus this quantity, what we get? This is 1 upon beta times of, and here we will have minus. Yeah. Okay, so 1 upon beta times of 1 divided by 1 upon beta minus t. Okay, so this is what we get. This is our mgf. Let us go back to the mgf of the gamma distribution that we have found. It is 1 upon 1 minus t beta to the power alpha. So let us try to simplify it and see what it is. 1 upon beta, okay, 1 divided by 1 minus t beta to the power, okay, in the numerator we have beta, so it is 1 upon 1 minus t beta. So we had power alpha in gamma distribution. Here we have let alpha equals 1, so this is it. Okay, so mean, so we will have to just differentiate it for one time and it for the second time. Okay, when we differentiate it for the one time, what do we get? We get minus 1 upon 1 minus t beta whole square product with minus beta, isn't it? So it is beta upon 1 minus t beta whole square. Okay, and the second derivative is minus 2 beta upon 1 minus t beta whole cube product with minus beta, so it is simply 2 beta square upon 1 minus t beta whole cube. So now that our mean is m prime at 0, which is nothing but simply beta, and expectation of x square is 2 beta square, which is the second derivative at 0. Okay, which implies variance of x is 2 beta square minus beta square, which is nothing but simply beta square. Okay, and for this exponential distribution, we can prove the lack of memory property as well. How are we going to do it? We just try to find out the distribution function fx of x. It is what? It is from 0 to x, isn't it? 1 upon beta e to the power minus t upon, okay, u upon beta du. So this 1 upon beta is a constant, so we take it outside, and this is this quantity divided by minus of u upon beta over the limit 0 to x. So when we substitute it, this beta goes to the numerator and this beta and beta gets cancelled. And when we substitute x, we get minus e to the power u upon x. Sorry, it is 1 upon beta, isn't it? Yeah. So it is x upon beta. Then when we substitute 0, we get 1. So plus 1. So it is 1 minus e to the power minus x upon beta. Okay. Now we need probability of x greater than t. Okay. Okay, let me write somewhere here. So probability of x greater than t means 1 minus probability of x less than or equals t. So this fx of x means what? It is the probability that x is smaller than or equals x. So 1 minus e to the power minus 1 minus of 1 minus e to the power minus t upon beta. So it is simply e to the power minus t upon beta. Okay. Now that you have this expression, now try to prove it. So probability of x greater than s plus t means e to the power minus s plus t upon beta. Right. And probability of x greater than s means e to the power minus s upon beta. Okay, when you divide these two things, of course you are going to get e to the power minus t upon beta. That is what the lack of memory property is. Okay, now coming to the example, it is said that the lifetime of an electronic component is an exponential random variable with mean 2 years. So our 1 upon beta is 2. What is the working probability that the component that is 1 year old and working will more for 2 more years? Okay, already the lifetime is 1 year and is working now. Okay, and it is going to work for more than 2 more years, which means it has to work for 3 years. Okay, we need to find out the probability with mean 2 years. It is given. So to denote a beta distribution, if we know the mean, that is beta value, it is more than enough to write down the density function. Here the density function is, what is our f of x here? It is 1 upon 2 e to the power minus x upon 2 for x positive. We are asked to find out the probability that your x is working, it is already 1 year old and it is working more for 2 years. That means it will have to work for more than 3 years. So it is, we have already calculated it, right? It is e to the power minus t upon beta. Here t is what? It is t is 3 upon 2. So you just need to find out this value. Since we have found it already, probability of x greater than t we have found, so we are just directly using it. That's it. Okay, if not, what do? We have to integrate from 3 to infinity, 3 to infinity f of x dx. This is what you need to find it out, right? So anyway, this is going to be e to the power minus 3 upon 2. Coming to the next problem, here it is said that the amount of time that a watch will run without having to be reset is a random variable having an exponential distribution and mean is given. We need to find out the probability that it will have to be reset in less than 20 days. So we will have to find out the probability that till 20, 0 to 20, what is the probability, and not have to be reset in at least 60 days. So greater than or equal to 60, we need to find it out. Okay, these two are the things that we are going to find it out. So we know the density function with which we can find out the distribution function. Okay, and through this we just calculate the probabilities. That's it. Thank you.